Today we're going to go over the standard normal distribution and the z-table. While there are many normal distributions for different means and standard deviations, there is only one standard normal distribution. We can convert any normal distribution to the standard normal distribution by standardizing. Standardizing involves subtracting the mean from a value and dividing the difference by the standard deviation, a linear transformation. Here's the formula for standardizing. Z equals x minus mu all over sigma. This is not on your formula sheet, so this is something you will need to know. The normal distribution with parameters mu equals 0 and sigma equals 1 is called the standard normal distribution. The standard normal distribution models standardized values, z-scores. The z-score tells you the number of standard deviations above or below the mean you are. Observations larger than the mean will have a positive z-score, and observations smaller than the mean will have a negative z-score. Along the sides and tops of the z-table are z-values, units, tenths, and hundredths. Each entry inside the table, the 4-digit number, represents the proportion of the area below, which means to the left of, a particular z-score. I call this the left shade curve. Now remember, you always need to draw a picture, shade, and label to get full credit on these problems. The next page is the actual z-table. You can find this in your formula packet. It's table A in your formula packet. You might want to print off this table because we're going to be referring to it throughout the notes. So the 4-digit numbers within this table here are the proportions to the left of the z-score. So here I have the z-score, it's the shaded area to the left, the shaded area to the left. So say, for example, I needed to find the shaded area to the right of the z-score. I would have to take 1, since the area underneath our curve is 1, and subtract this side if I needed to find the area to the right. So let's go through some problems that are already standardized for us so that we can learn how to use the table before moving on to using the calculator to find the area. So let's look at number 1, the area line to the left of z equals 1. So the first thing you need to do is you need to actually draw a picture of this. So you need to draw your normal curve with 0, and each one of these will be a standard deviation. And it's to the left of z equals 1. So here would be z equals 1. And to the left would be all of this area to the left. So then what we do is we go to our table. We find z equals 1. Notice it starts at negative 3.4 and then goes all the way to the positive. So z equals 1 would be right here. 1.0 would be this value that I have right here. And I have 0.8413. So my answer to this one would be 0.8413. So now let's look at number 2, the area line to the left of negative 2.5. So again, you need to draw your normal curve. And this would be to the negative 2.5. This is negative 1, negative 2. Negative 2.5 would be here. And it's to the left. So again, you would go to your table. We would look for negative 2.5. Negative 2.5 is here. It's negative 2.50 because we have 0, 0 here. So it'd be this value here, 0.0062. And let's look at number 3. Area line to the right of z equals 1.79. So 1.79 would be about here. And it's the area to the right of 1.79. So my table uses just the area to the left. So to find the area to the right of 1.79, it would have to be 1 minus whatever I get for the value of 1.79. So go into my table, I look for 1 over here. So here I have 1, and then I need to go down to 1.7 and all the way over to 0.9. And I have 0.9633. So I'd have 0.9633 here. So I have 1 minus 0.9633 would give me a value of 0.0367 would be the proportion of the area underneath the curve. So again, these are already standardized for us. So we're just learning to use the table on these. So the next one, the area to the left of negative 1.79. So again, I would draw my normal curve. I would go ahead and put in negative 1.79. Here's negative 1. Here's negative 2. Negative 1.79 would be about here. Shade in my area, and it's the area to the left. So I'd go ahead to my table. I'd find negative 1.7, go all the way over to the 9, and I get 0.0367. So my answer would be 0.0367. And the last one is the area line between negative 1.53 and z equals 2.05. So I would have negative 1.53, which I would label here, and 2.05 is the area between, so I would shade that area between. And here we have to do the 2.05 minus the negative 1.53 to get the area in between. So first I'd go and look for 2.05. So 2.0 is here. 2.05 would be this one right here, which is 0.9798. So I have 0.9798 minus, now I have to look for negative 1.53. So negative 1.5 is here. 1.53 would be this one, which is 0.0630. And I'd subtract those two, and I get an area of 0.9168 would be my answer. And that is how you use the table. So now let's look at an example. So this example is not included on your paper, so you might want to actually write it on the back. Some IQ tests are standardized to a normal model with mean of 100 and standard deviation of 16. And that is denoted by n and then the parentheses 116, with this being your mean and this being your standard deviation. And we went over that in the notes. So A, what percent of people should have IQ scores below 105? So the first thing that we want to do is we want to draw a picture of this. So when I draw a picture, you start with your normal curve. So you always must draw a picture. My mean is 100. And my standard deviation is 16. So if I was counting out 3 standard deviations, this would be 116. And then this would be 132. And then this would be 148. Going backwards, this would be 84. The next one would be 68. And the last one would be 52. You don't have to write those each time, but if you were to draw those in, that's what it would look like. I want below 105, so we know 105 is right about here. So I would draw that in, I would label 105. And below would be all this area shaded to the right, or to the left, excuse me. So we need to find our z for this, and z would be x minus mu over sigma. So my z would be 105 minus 100 all over 16. I put that in my calculator, and I get 0.3125. So we're finding the probability or the proportion underneath the curve. So the proportion that x is less than 105 is the same as z is less than 0.3125. So then we go to our table, and it would be 0.31. So I'd go over to 0.3, and 0.31 would give me 0.6217. So my proportion would be 0.6217. So what I would say is, according to the model, about 62.17% of IQ scores are below 105. Okay, let's look at the next one, B. What percent of people should have IQ scores above 120? So again, you first want to draw a picture. And we have 100 here, and then 120. And it would be above 120. First, you need to find your z. So it'd be 120 minus 100 all over 16, which would be 1.25. So the proportion of x is greater than 120 would be the same when I standardize it. The probability that z is greater than 1.25. And this would be 1 minus, because it's to the right instead of to the left, so we'd be 1 minus. And we would have to go look on our table at 1.25. So 1.25 would be right here, 0.8944. And that would be 0.1056. And then the last one, what percent of people should have IQ scores between 90 and 110? So again, you go ahead, you draw your normal curve, 100's in the middle, 90 and 110. So 90 would be about here, 110 here. Shade the middle section, find your z. So this one would have two z's. So we'd have 90 minus 100 all over 16, which equals negative 625. And then z, our other z would be 110 minus 100 all over 16, which would be 0.625. So the probability that 90 is less than x, which is less than 110, equals the probability that negative 0.625 is less than z, which is less than 0.625. And then when you go to your table, when you look at negative 6.25, you would get 0.7357 minus 0.2643, and we would get 0.4784. I believe that is. 14. And again, you should answer these with according to the normal model. About 47.14% of the IQ scores fall between 90 and 110. So according to the normal model, about 47.14% of IQ scores fall between 90 and 110. So I want to look at chapter 6, number 33, normal cattle. So using the normal model, 1,152 and 84, the normal model of weights of Angus steers in exercise 17, what percent of steers weigh over 1,250 pounds, under 1,200 pounds, and between 1,000 and 1,100 pounds? So let's go ahead and do this one together. Or better yet, why don't you take a minute, since we're looking at 33, and pause this video and do that one on your own. Okay, so A was over 1250. So you need to go ahead, draw your normal model. So we have our mean of 1,500 or 1,152 over 1250. So 1250 would be here. Over 1250 would mean we would shade this side. And first, we would need to standardize this. So we'd have z equals x minus mu all over sigma. So z would be 1,250 minus 1,152 all over 84. And I get a z of 1.167. So probability that x is greater than 1,250 is equal to the probability that z is greater than 1.167 would be 1 minus whatever I get for 1.167. So I go over here and I would find 1.6 and 1.167, so that's about 1.17. So 1.17 would be about 0.8790. And that would give me about 0.121. So your final answer would be according to the model. So that means this area here is about 12.1%. So you would say according to the normal model, about 12.1% of steers are expected to weigh over 1,250 pounds. So let's look at B. B was under 1,200. So I have 1,152 here. 1,200 here, and under would look like this. So you find your Z, and you would have 1,200 minus 1,152 all over 84, and we would get 0.5714. So this would be the probability of X is less than 1,200 equals the probability that Z is less than 0.5714. And then go into your table. So we go to 0.57, and you get 0.7157. So you would say, according to the normal model, about 71.57% of steers are expected to weigh under 1,200 pounds. And then the last one, C. Between 1,000 and 1,100. Again, you always need to draw your normal curve. My mean was 1,052. This is between 1,000 and 1,100. I would find my Z's. 1,000 minus 1,152 all over 84. That would give me negative 1.810. My other Z would be 1,100 minus 1,052 all over 84. That would give me negative 0.619. So the probability that 1,000 is less than X, which is less than 1,100, When I standardize it, it would be the probability of negative 1.810 is less than z, which is less than negative 0.619. And then you would go to your table. You should have went to your table to find the values and subtracted them, and you should have, when you subtracted them, get 0.233. So you should say according to the model, the normal model, about 23.3% of steer will weigh between 1,000 and 1,100 pounds. Let's look at one more example. I'm going to look at number 41 from chapter 6, and we're going to do A through C. Assume the cholesterol levels of adult American women can be described by a normal model with a mean of 188 and a standard deviation of 24. Draw and label the normal model. What percent of adult women do you expect to have cholesterol levels over 200? What percent of adult women do you expect to have cholesterol levels between 1,500 or 150 and 170? So the first thing with A is they want us to draw the normal model. So you should draw with the normal model. So all of this is the normal model of 188 is our mean and 24 is our standard deviation. For A, we want to draw 3 standard deviations from the mean using our normal model. So this is the cholesterol level with my mean of 188. One standard deviation above the mean would be 212. 2 standard deviations above the mean would be 236. And 3 standard deviations above the mean would be 260. 1 standard deviation below the mean would be 164. 2 standard deviations below the mean would be 140. And 3 standard deviations below the mean would be 116. Then B, they wanted how many are expected to be above 200. So again, draw your normal model. My mean of 188. Above 200. So I have 200 here. I would find my Z, which would be 200 minus 188 all over 24. I get 0.5. So the probability that X is greater than 200 would equal the probability that Z is greater than 0.5, which would be 1 minus, and I would have to go to that. When I find 0.5 on here, I get 0.6554, or no, 0.6915. And that would give me 0.3085. So again, you would say according to the normal model, 30.85% of American women are expected to have cholesterol levels above 200. and then C was between 150 and 170. So again, you always have to draw a picture. My mean is 188. $150 and 170, and it would be the area between. So we have to find two z's. So I'd have 150 minus 188 all over 24, and I'd get negative 1.583, and I have z equals 170 minus 188 all over 24, and I get negative 0.75. So this is the probability that 150 is less than x, which is less than 170. When I standardize it, I get my z-scores of negative 1.583 is less than z, which is less than negative 0.75. And you go to the table, subtract the 2, and you should get 0.17. So again, you'd have to state according to the normal model, about 17% of American women are expected to have cholesterol levels between 150 and 170. And again, this is all using the table. So with your graphing calculator, you can go ahead and use this instead of using the table. And this is on page 112 in your textbook. So you need to make sure that you pay close attention to pages 111 to 113 to get help with all this. Specifically, page 112 gives you calculator help. So if it's standardized, use normal CDF, the lower z-score, then the upper z-score, and it will give you the area under the curve. If it's not standardized, use normal CDF, your lower value, your upper value, then the mean and standard deviation with the commas. And this is described on page 112. If you have questions about using your calculator, we can go over that in class. You need to make sure you have specific questions at the beginning of class.